Unit 7, Chapter 26, Linear Regression, T-Test, and T-Interval. We have finally come to the very last test of our hypothesis testing unit, and it is the linear regression. You have been taught the linear regression, doing a y hat equals the mx plus b, which is the algebra way that you did it, but you've been taught that before, and now we're going to put it to the hypothesis test. Okay, so let's just kind of go over the theory first. And so for regression for inference, you're going to model the relationships between two quantitative variables. Now, the chi-squared that we did were categorical. We were saying, what categories of M&Ms do you have? You have blue, yellow, red, and all the different types. Now we have quantitative, because the only type of variables that you can actually put into an XY graph are obviously quantitative. You can't have red on the x-axis and frequency on the y-axis and get a linear relationship. That would only get a histogram. So this one would have to be, which we're about to do, is body fat percentage, which is a quantitative measure, and the number of men, which is a quantitative measure. And you would get a linear relationship, and this here is the frequency of men, because it's showing something else. But if I was doing, which it's going to show in just a second, is your waist size and body fat percent, you would get an actual line. Okay, so you know, of course, that this is the actual data, and this regression line is the LSRL, least square regression line, and that is basically my predictor of any data that's going to have this particular waist size, and that's going to be the predicted body fat for the predicted waist size. And mine's a little crooked. It should be obviously a little straighter. All right, so let's go ahead and go through here. We know that every population data won't line up perfectly straight, so that's what this is doing, is this is taking this particular histogram is only for men with 38-inch waist. So it says for 38-inch waist, what do you actually get? You're actually going to get, most men have about 20% body fat, but it goes up to 30% and down as lean as 10%. But obviously most has 20%. So if you were to actually graph this is what it would look like. If this is my let's say this is 34-inch, 36-inch, 38, 40 or 42, something like that. It's showing each waist distribution is going to have each waist value is going to have a different distribution of body fat. So what we're trying to do is we're trying to come up with a regression line that's going to be an accurate prediction. And so my prediction line is written where this is where we're using beta as my value of my true population slope. And we're using B1 as my slope for my sample. And then we use B0 as my y-intercept for my sample. And you can see this is mu y, that's a mu y is what that is. And that would be from the population. And so obviously you can see B0 as the true population slope, and I should have said B1 as my true population slope, and B0 as the true y-intercept from the population. Okay, so we have to do our conditions, and I'm going to jump to those in just a bit, but my conditions are linear, and these conditions, some of them are actually, and I explain them in a little bit easier detail later, so I'm going to just kind of skip this and go to the next part, and you can see those conditions. But basically, we're going to go from here, and you can see that what it's doing is I'm trying to see if all my errors, that's what these are, the errors. And are the errors normal? Do they have a normal model for the errors? And and then the errors also have to be independent from each other. I have to have a straight enough, which is linear, and I have to have the standard deviation around the true regression line has to be constant, where it's going to be a equal spread. And of course, the errors are going to be a normal model. Okay, so to be able to do this, we're going to go ahead and I'm going to show you from our linear regression Phantom's Panic. So I gave everyone one of these here, and I'm just going to walk us through it once I go through the data. So let me just kind of backtrack and look at the data here. Most of the linear regression tests you're ever going to do, it gives you a data output. Yes, you can they can give you a data and you put it in, and if you want to watch how to do that, you can go to my video that shows how to put linear regression in from raw data and how to run a linear regression test. It's quite easy. You put your X in the spreadsheet, you put your Y in the spreadsheet, and that's it. Then you run a stats test and everything is done for you from there. A lot of great information, and all of this data comes out in that information. However, most of the times for the test, they go ahead and just give you the data output. So I want to make sure you know what all these things are. So let's look at here. So the slope is B1, and and from this, it's located right here, 1.69997, and it's always here in the second column under coefficient. That word also might say constant. All right, so the y-intercept is B0, and that one is this value here of the 42.73341. The confidence interval is actually from my B1, my slope of the 1.6997, and also combination with the standard error. So you can see it's the B1 plus or minus the T star, which you find T star inverse T. Let me do a quick review on inverse T. And the area is the confidence interval plus the tail. So whatever the tail is, you got to make sure you get that probability. And then the degrees of freedom. And by the way, the degrees of freedom here, which I tell you in just a second, are n-2. Okay, the test statistic is T. And sometimes it's called T ratio, sometimes it's called T. So that's your test statistic, 22.9. But what's kind of cool, if you can see 1.6997 divided by 0.0743 is equal to 22.9. So you can see right here that T is equal to the slope divided by the standard error, because remember, it's statistic minus parameter divided by standard error is going to be my T. Well, my parameter is beta, and in the HO, my beta is equal to 0. So that's why this ratio works out. Okay, the linear regression equation is just this here. It's just going to be, what I'd like to do is just show you guys that it's this here. And if you notice that I already put a plus sign here and parentheses, because that's what it is. And I go ahead, and if you put in your variables, then you don't have to define them. Okay, the coefficient of determination, that's my R squared, and it's up here. It usually says R squared, or it has a symbol R squared here. The next one is my correlation coefficient, and the correlation coefficient is R. And remember, it's positive if the slope's positive, and it's negative if the slope's negative. And be careful, because obviously, whenever you find the square root of R squared, you're going to get a positive number. But just make sure you notice if you have a negative slope, you're going to have a negative correlation. So just double check and make sure you check what your slope is. All right, your p-value is located right here. And it usually says probability or p-value. And the p-value is two-sided, so take note of that. And most of our linear regression tests are two-sided, but if they are a one-sided test, make sure that you divide your p-value by 2. Degrees of freedom, as I just discussed, is n-2. And the standard deviation of residuals is SE, and it's located up here. It says S or SE. And the standard deviation of residuals, remember, is just if the blue dots are my actual data, the line is my linear regression line, and the pink lines are my residuals. The standard error of the residuals is the average length of those lines, the average error that those dots are from the regression line. Okay, and the test statistic again, one more time, to get that 22.9, to get this 22.9 here, remember, is the 1.69997 divided by 740, or 0.0743. That the 0.0 just came off. And recall that the p-value is two-sided. So if you have a one-sided, you have to just pretty much divide the 0.001 divided by 2 to get that, because you can see that together it's 0.0031, 3 zeros and a 1, and divide it by 2 and you get 4 zeros and a 5. Just also make sure you see that r-squared adjusted is ignored if it's up there, and then the top line of the y-intercept, that's also ignored, the one I already have crossed out. The reason that's crossed out is because it's all the information of regression on intercept, and we're not studying intercept, and we don't study intercept in this course. The only thing that we study is slope in this course. Let me go ahead and go to an example for you. This one is one in your packet. It's GPA versus ACT, and I'm going to run a test for you. So if you run this test, it typically does, AP College Board does give you the data, and you're welcome to put this in the data as X and as Y, and then run a linear regression t-test, and put X in for X and Y in for Y, and it does everything for you. It's very, very easy. But you don't need to do that, because what College Board did for you is they went ahead and gave you the data, and it gave you the regression line, it gave you the residual plot, and it gave you a graph of your residuals. So looking at your conditions, which I'll jump to your conditions real fast just so you can see what I'll be doing. Your conditions are on your Phantom's Panic, but we have to have linear, which L stands for linear. I have to see if it's straight enough, and the residual plot is a random scatter. Independent, I have to check the 10% rule for independence. As I just discussed, my normal model has to be, my residuals have to be dispersed in a normal fashion. Or you can check your probability plot, which would be straight. Another thing you'll see is you might see a dot plot instead. You might see this instead of a histogram. Equal variance is just making sure that this is not good. You need where the errors, the standard deviation, you can call it equal standard deviation or equal variance. You need to make sure that the residual plot basically has an equal distance from all the way across. That's why this is not good, because it looks like kind of like a cheerleading megaphone, and this is a really accurate line, and then the line gets less accurate as it goes on. And then of course a random sample if you're going to be making conclusions beyond your sample. Okay, so let's continue for this example. So let's go ahead and run the test. So I'm going to say my P for my parameter is going to be beta equals the true slope of the population of least squared regression line for GPA and ACT. All right, and my beta is equal to 0, or my beta is greater than 0, because it says, do the data provide statistical evidence that there's a positive linear relationship? So that's why it's greater than. If you wanted to cut this out, you could cut that out if you just put in what's in red here. You're welcome to do either one. If you have the blue part though, you need to make sure you define that. My assumptions and conditions right here are linear, and you can see that the scatter plot is fairly linear. So right here, this is the scatter plot. Independent, you're going to check your 10% rule. Individual observations are independent. And then normal, you have to look at this shows a dot plot of the residuals right here. And you have to see if it's fairly symmetric with no strong skewness and no outliers. And that's basically what I was looking for. And equal standard deviation, which is equal variance or equal standard deviation, and it says the residual plot shows a similar variability. So basically, if you notice, I have about the same length on the top and the bottom throughout the whole set of data. And then random, it's a random sample of 9, which was given to me in my original setup, which was right here. Okay, so then N, I'm going to name the test. And the test is named later on, but I'm going to go ahead and name it. And it's a linear regression t-test with a degree of freedom of 9 minus 2 equals 7, because it's n minus 2, and I have a random sample of 9. Okay, so for my statistic, it's just this formula right here, but you do not have to use this formula. Instead, you're going to just put the data actually in, which we're going to get from our chart. So let me show you where that 7.507 is. That's just my slope. So when I go up here, I see this here's my slope, 7.507, and then that's my standard error. So it's just, remember, this divided by this gets me my t of the 5.82. So that's all you would do, is 7.587 divided by 1.29 equals 5.82. You don't have to draw the sampling distribution, because what we're really interested in is, since we don't know sigma, we need to use the t-distribution anyway. So you can just go ahead and do the t-distribution. And you're going to draw it, and you're going to label it T7. You're going to label this here, and then make sure this is labeled as your p-value. And when you get your p-value, you get 0.00335, and that is also located here. And you're like, wait a minute, that's 0.006. Yes, because remember, this is two-sided, which would be a not equal to, which would be a not equal to. And remember, when we go back to our our alternative hypothesis, it was greater than, so I had to divide it by 2. Finally, to interpret, assuming this is interpreting the p-value, so let's go to the decision and conclusion first. Because p is less than 0.05, we reject home. We do not have convincing evidence of a positive linear relationship between GPA and ACT. Make sure you use context, otherwise you won't get full credit. If you are interpreting your p-value, what p-value means is assuming ho is true, which is beta equals 0, there is a point very tiny, which is p-value probability, of getting a sample slope of, this is what we got from my sample, that was my slope here, of this or greater purely by chance. The notes here for you to make sure that you get is that you have your phantoms. Of course, this is just done as phantoms. And then you have your test statistic, which is beta minus, or b minus beta over standard error with a degree of freedom of n minus 2. And that's it for here. Also, let me just show you the answers for this one. This is the check for understanding. And what you're doing here is the same thing. Remember, let's just check where you got your data from. This is my slope, and you can see that's there, my slope. This is my standard error, and you can see definitely here, it's where I got my standard error from, a nice little shape. This is my t, because remember, the slope divided by standard error equals this here. And the reason you're going to need to know that is sometimes you actually have a data chart that looks like this. It doesn't give you the t, and you actually have to find the t yourself. And the p-value, which you would use, by the way, this is just kind of a side, if you are not given the p-value because you're not given that part of the data, you can use TCDF in your calculator. And your lower bound would be your t-value, and your upper bound would be infinity, and of course you get your degrees of freedom. So then this is the same thing as I have a p-value, a high p-value, so this is a fail to reject. So you can go ahead and read through those. Okay, let me just go through quickly just on the confidence interval for linear regression. So you're going to do the same thing. You're going to just define beta, and we're doing a 90% confidence level. You're going to do liner just like we did before, so I'm not going to go over that again. You can read that on your own. But I just wanted to show you where all this is. Your point estimate, or on your chart, it tells you your statistic, and your statistic is B, your slope here. And this is in the same spot, so there's my slope, and then that's my standard error. So it's going to be the standard error and my slope, which is the 30.4, and then the 2.04. Where that 1.734 comes is that t star, and for the t star, you're going to go to your calculator, inverse t. The area, remember, it's the confidence interval plus the tail. The confidence interval is 90%, and the tail is 5%, so you're going to put 95. And then the degrees of freedom, you can look here, and you see the degrees of freedom Let's see how many we have. It should tell you, there you go, 20. And it's a linear regression, so it's 20 minus 2, which is 18. And that will get you at a 1.734. So notice I get my confidence interval here, and I conclude that my interval captures the true slope of the LSRL for number of balloons of X and Y, which is number of balloons and weight. All right, I hope that helped. If you need help of how to put linear regression into the calculator, go ahead and go to my video. But remember, most of the time, like, I've never seen an actual one that you actually have to put it in your calculator, but it is a handy tool to have to be able to put it in your calculator and to be able to find the regression line and then find the residual plot of your excuse me, not regression. This is the regression line, but also the residual plot. It'll give you a histogram or a dot plot of the residual plot. All right, thank you very much.